Good morning all. This is Dr. T. Khalandar Basha, working as Associate Professor in Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the bit addressable feature in 8051 microcontroller. This topic is under the course Microprocessors and Microcontrollers. The slides are prepared by referring the textbooks. The 8051 microcontroller by Kenneth J. Ayala, publication Cengage Learning. So many microprocessors allow program to access a register and I/O ports in byte size only. So the data transactions will be takes place either through I/O ports or through the processor or register. The size of the data which we are going to be takes place is of 8 bits. However, in many applications we need to check a single bit where the one unique and powerful feature of 8051 is a single bit operation. Single bit instructions allow the programmer to set, clear, move and complement individual bits of a port or memory or register. So it is registers or RAM and I/O ports that need to be a bit addressable. RAM holding a program code for execution, it is not bit addressable. Whereas few registers, some of the memory locations of RAM, I/O ports that can be bit addressable. Say in 8051 microcontroller, what are the RAM which are existing? The memory addresses from 202 to 2FH. These addresses of RAM are used as bit addressable RAM locations. This 16 byte provide 128 bits of RAM bit addressable. Since it is 16 memory locations, each memory locations of 8 bit size, that is 16 into 8, which is 128 bits we can access bitwise. We can also refer these bits as 0 to 127. In the hexadecimal, we can take this one is from 00 to 7FH. So the first byte of internal RAM location, that is 20H, has the bit addressable that is from 0 to 7. So this 20H location, we are going to have the address is from 0 to 7H. The last byte, that is 20 to 2F, we are having. This 2F location will have the addresses having starting from 78H to 7H. The internal RAM locations from 20 to 2F, these either we can go for byte addressable as well as bit addressable. So the bit addressable, that is from 00 to 7F, belongs to the RAM address from 20 to 2FH. The bit addressable above this, like 80H to F7H, are belongs to SFRs like port 0, port 1, etc. So this is total general purpose RAM, which is having the starting address is from 0 to 7H. Out of this, all the memory locations are byte addressable. From 00 to 07, we are going to have R0 to R7 registers, totals 8 registers. This we can consider as bank 0. Next, from 08 to 0F, again it is a register bank 1. Here also we are going to have the register is R0 to R7. On the top of this, again 8 locations are corresponding to 8 registers of bank 2. On the top of this, we are going to have R0 to R7, which is bank 3 registers. From the address 202, 2F, these locations we can use as bit addressable as well as byte addressable. If you are taking as bit addressable, 00 location, 01, 02, 03 like this until 7F we have. On the top of this, that is from 30 to 7F, these are used again as a general purpose RAM. Find out to which by each of the following bits belongs to. Give the address of the RAM byte in hexadecimal. So first we are going to check set B 42H, clear 67H, clear 0FH, set B 28H, clear 12H, set B 05H. So first one, the 28H location is corresponding to the 42 location. So if you want to set B 42H, where the 42H is nothing but it is having a bit at 28 memory location. In the 28th memory location, D0, D1, D2 bit. So it is nothing but the D2 bit of RAM location 28H. Similarly, the next one is for clearing 67H. So 67 is corresponding to the D7th bit, D0 to D7th bit, the D7th bit of 2CH. Next one is clear 0FH. The 0FH is corresponding to the D7th bit of 21 location. Next one is for 28. 28 is the D08th bit of 25th memory location. So the next one is corresponding to 0CH, where 0CH is the D4 bit of 21H. The next one is corresponding to 05H. 05H is nothing but the D5th of the 20th location. So to avoid confusion regarding the addresses from 00 to 07H, the 128 of a RAM have byte addressable from 00 to 7H that can be accessed in byte size using various addressing modes like a direct and register indirect addressing modes. Whereas the 16 bytes of RAM location, that is from 20 to 2H, has the bit addressable from 00 to 7H. So we can use only the single bit instructions, and these instructions use only direct addressing mode. So the instructions that are used for a single bit addressing operations are set B bit. So this instruction is used to set the particular bit whichever is specified in the instruction. Clear bit, it is for clearing the bit. So after executing this, whatever the bit which was specified, that will be cleared. Next, CPL bit, which is for complement bit. So complement the bit. So whatever the bit which you have mentioned in the instruction, that will be complemented. Next one is JB bit target. So JB stands for jump if bit. So this is a two operand instruction where the first operand is bit for which we are going to check. So if it is true, jump if bit, that is if bit is equivalent to 1, then the control will be transferred to the target location. Otherwise, the subsequent instruction will be executed. JNB bit target. Here, we are going to check the bit that is for not a bit, which indicates if the bit is equivalent to 0, then jump the control to the target address specified in the instruction. JPC bit comma target. So jump to the target if bit is set and clear the bit before the jump. Well, all the SFRs which are registers are byte addressable, as well as a few of the SFRs are bit addressable also. The ports, that is from port 0 to port 3, which are byte addressable as well as bit addressable. So we can access either the entire 8 bits or only a single bits of ports, that is port 0, port 1, port 2 and port 3, without altering the rest. So as it is possible for port bits for byte addressable as well as bit addressable, when we are accessing bit addressable, the rest of the bits will not be altered. So when accessing a port in a single bit manner, we use the syntax like set B, port number and bit number. So this indicates which port you are accessing, whereas the bit corresponding to port, bit of the. So X can take either port 0, port 1, port 2 or port 3, whereas Y will take the number where it is corresponding to the bit from 0 to 7 for the data bits on D0 to D7. So let us consider example set B P1.5. So here the instructions which we are using for set the bit, which bit we are going to set? The port 1, the D5 bits. So out of the port 1, this is D0, D1, D2, D3, D4, D5, D6 and D7. So here we are going to alter only this particular bit. So after executing this instruction, this bit will be 1, the remaining bits will not be altered. Notice that when code such as a set B P1.0 is assembled, it becomes a set B 90H, where 90H is the address of the port. So the bit address for IO ports, we can consider for port 0, 80 to 87H, whereas for port 1, 90 to 97, whereas port 2 to A0 to A7, for port 3, B0 to B7. So the port 0 will varies the address for bit addressable from 80H to 87H. Whereas for port 1, it is 90 to 97H. For port 2, A0H to A7H. Whereas for port 3, B0H to B07. Next, we will see the SFR RAM address for byte and bit addressable. Here, if you observe, this is a accumulator. The bit addressable, that is from 80 to 7FH, belongs to SFRs, port 0, TCON, port 1, SCON and P2, etc. So the address for accumulator is E0. The E0 bit to E7 bits we can access. Similarly, program status word, we are having the address is D0. So D0 to D7 are bit addressable. For instruction interrupt priority, that is IPSFR, will have the address is B8. So this interrupt priority, only 5 bits will be used for giving the prioritize for interrupts. So we use only B8, B9, BA, BB and this. Next one is for port 3, which are at the address B0 from B0 to B7. Next, for enabling the interrupts, that is IESFR, which will have the addresses from A8 to AF. Next, for port 2, whereas for port 2, we can use, it is a bit addressable from A0 to A7. When it comes to SBUF, that is serial bus transmission, the data will be stored in a buffer, serial buffer. So it is not a bit addressable where the data will be transferred 8 bits to. Whereas SCON for control, serial control, we have the addresses from 98 to 99, which are bit addressable as well as byte addressable. For port 1, the address is 90 to 97 if it is bit addressable. If it is byte addressable, it is 90H. Whereas the registers for timers TH1, TH0, TL1, TL0, T mode, and PCON. These registers are byte addressable. We can't access bit by bit. Whereas the TCON register for timer control, it is a bit addressable from the address 88 to 8FH. The data pointer DPH and DPL stack pointer SP are not bit addressable, whereas they are byte addressable. Next one is port 0. The port 0 is bit addressable as well as byte addressable. If it is bit addressable, we use the address from 80 to 87H. If it is byte addressable, we can use 80H as the address for port 0. So the registers accumulator, B, program status word, interrupt priority, interrupt enable, accumulator, SCON register and TCON registers are bit addressable, while all IO ports are bit addressable. In PSW, program status word register, 2 bits are selected aside for selection of the registers banks which are present in the RAM. So it is consist of 4 registers banks: register bank 0, bank 1, bank 2, bank 3. So this will be selected in the program status word by selecting the bits P, RS1 and RS2. These two for a selection of the register bank. 2 bits are there. So 00, bank 0 will be selected. That is, the address is from 00 to 07H. 01H, register bank 1 will be selected, which are having the addresses 08 to 0FH. When RS1, RS0 is equal to 10, register bank 2 is selected, which are having the addresses 10H to 17H. Next, when RS1, RS0 is configured as 11, register bank 3 will be selected, where the addresses for this register bank is from 1F to 18 to 1FH. Each register bank is of 8 registers we are going to have, that is from R0 to R7. So upon a reset, the default is bank 0 is selected. If you want to select any another register bank like bank 1 or bank 2 or bank 3 apart from bank 0, then we have to configure the RS1 and RS0 bits of PSW. Now we will see a sample programs. Write a program to save the accumulator in R7 and it is for bank 2. So for bank 2, we have to write the RS1 bits as well as RS0 bits as 10. So we have to clear the RS0 bit and we have to set RS1 bit. So in PSW, D0, D1, D2, D3. So the D3 bit and D4 bits we have to clear or set depending upon which register bank we are going to set. So for making a register's RS bit 0 for selecting a bank 2, we have to clear PSW3. To set RS4 as 1, we are going to set PSW4. So once we have set these two values for PSW3 and 4 as 10, then the bank 2 will be selected. Once the bank 2 is selected, we can have the data transaction. So here we need to transfer the data, save the accumulator in R7. So accumulator contents would be moved into R7, where this R7 belongs to a register bank 2. Next, write a program to see if the RAM locations 37H contains an even value. If so, send it to P2. If not, make it even and then send it to P2. So here we have to fetch the addresses of 37H. Then we are going to check whether the accumulator content is even or odd. So the 37 location, first we are going to be loaded into accumulator. Then we will check whether the accumulator content is even or odd. So for even or odd, by checking the LSB bit, we can decide. If the LSB bit is equal to 0, it indicates it is a even data. If it is 1, it indicates the accumulator contains the odd data. So first we will move the 37 memory location contents into accumulator. Here we will check JNB accumulator.0. So we are going to check the LSB. If jump if no bit, it indicates. So if the D0 bit of accumulator is 0, then it is going to jump to the label 1. Otherwise, go for increment. Right. After these two operations, the accumulator contents we want to move to P2 port. Next, we can have the directive, which is a bit directive, which is used widely to directive to assign the bit addressable IO and RAM locations. So allows a program assign the IO or a RAM bit at the beginning of the program, making it easier to modify them. So let us consider a switch is connected to port 2.0 and LED is connected to P3.7. Write a program to get the status of the switch and send it to LED. So this LED we are connected to LED is connected to 3.7. The switch is connected to 2.0. Then move C, SW. So instead of referring as P3.7, we can refer or P2.0, we can refer with SW. Move C, SW. The switch position will be moved to C. Then this C value will be moved to LED, which is nothing but we are moving directly to P3.7. So for a repetition of this, we can go for short jump to the label here, where at the label, read the switch position, the corresponding value will be placed to the LED. Next one is we can use the equate directive, that is EQU, for assigning the address defined by names like a P1.7 or P2, defined by addresses like 97H or 80H. The switch is connected to P1.7. The switch is connected. Write a program to check the status of the switch and make the following decision. If switch is closed, send 0 to port 2. If switch is equivalent to 1, then send 1 to port. So first we will assign P1.7 to a switch by using equative directive SW equate P1.7. The next one is my data is equated to the port 2. First we have to read the switch position. So for that we'll write move C, SW. This will read the switch position. If switch is equivalent to 1, then we have to send 1 to port 2. So if carry is equivalent to 1, then control will be transferred to the label over, where 1 will be moved to the port 2, which is pointed by my data. Next, for continuous, we go for S jump. Here it is a continuous looping taking. So let us consider if the switch position is 0, then this condition is fails. Then we are going to move 0 to the my data, where my data is nothing but port 2. So either of case, we want to go for a repetition of the loop. Then we will write S jump here. So thank you. In this session, we have discussed the bit addressable features in 8051 microcontroller. So what are the memory locations which we can access as byte addressable only, and which we can access both bit addressable as well as byte addressable. We have seen few SFRs discussed which are allowed for accessing bitwise as well as bytewise, and which are the registers which are not feasible for accessing bit addressable also we have discussed. And few related programs also we have checked. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.